What we're going to do in this video is start talking about forces that exist between even neutral atoms or neutral molecules. And the first of these intermolecular forces we will talk about are London dispersion forces. So it sounds very fancy, but it's actually a pretty interesting and almost intuitive phenomenon. So we are used to thinking about atoms, and let's just say we have a neutral atom, so it has the same number of protons and electrons, and so that's all. Those are all the protons and the neutrons in the nucleus, and then it'll have a cloud of electrons. So I'm just imagining all these electrons kind of jumping around. That's how I'm going to represent it. And let's imagine, and this is definitely not drawn to scale. The nucleus would actually be much smaller if it was. But let's say that there is an adjacent atom right over here, and it's also neutral. Maybe it's the same type of atom. It could be different, but we're going to say it's neutral. And it also has an electron cloud. And so if these are both neutral in charge, how would they be attracted to each other? And that's what London dispersion forces actually explain, because we have observed that even neutral atoms and neutral molecules can get attracted to each other. And the way to think about it is, electrons are constantly jumping around probabilistically. They're in this probability density cloud where an electron could be anywhere at any given moment, but they're not always going to be evenly distributed. You can imagine that there is a moment where that left atom might look like this, just for a moment, where most of, or maybe slightly more of the electrons are spending time on the left side of the atom than on the right side. So maybe it looks something like that. And so for that brief moment, you have a partial negative charge. This is the Greek letter delta, lowercase delta, which is used to denote partial charge. And on this side, you might have a partial positive charge. Because remember, when it was evenly distributed, the negative charge was offset by the positive charge of the nucleus. But here on the right side, because there's fewer electrons here, maybe you have a partial positive. On the left side, you have, where most of the electrons are in that moment, partial negative. Now, what might this induce in the neighboring atom? Think about that. Pause the video. Think about what might happen in the neighboring atom then. Well, we know that like charges repel each other and opposite charges attract each other. So if we have a partial positive charge out here on the right side of this left atom, well, then the negative electrons might be attracted to it in this right atom. So these electrons here might actually be pulled a little bit to the left. So they might be pulled a little bit to the left. And so that will induce what is called a dipole. So now you'll have a partial negative charge on the left side of this atom and then a partial positive charge on the right side of it. And we already had a randomly occurring dipole on the left-hand side, but then that would have induced a dipole on the right-hand side. A dipole is just when you have the separation of charge, where you have your positive and negative charges at two different parts of a molecule or an atom or really anything. But in this world, then all of a sudden, these two characters are going to be attracted to each other, or the atoms are going to be attracted to each other. And this attraction that happens due to induced dipoles, that is exactly what London dispersion forces is all about. You can actually call London dispersion forces as induced dipole forces. They become attracted to each other because of what could start out as a temporary imbalance of electrons, but then it induces a dipole in the other atom or the other molecule, and then they get attracted. So the next question you might ask is, how strong can these forces get? And that's all about a notion of polarizability. How easy is it to polarize an atom or molecule? And generally speaking, the more electrons you have, so the larger the electron cloud, which is usually associated with molar mass, so usually molar mass, then the higher polarizability you're going to have, because you're just going to have more electrons to play around with. If this was a helium atom, which has a relatively small electron cloud, you couldn't have a significant imbalance. At most, you might have 2 electrons on one side, which would cause some imbalance. But on the other hand, imagine a much larger atom or a much larger molecule. You could have much more significant imbalances, 3, 4, 5, 50 electrons. And that would create a stronger temporary dipole, which would then induce a stronger dipole in the neighbors. That could domino through the entire sample of that molecule. So, for example, if you were to compare some noble gases to each other, and so we can look at the noble gases here on the right-hand side. If you were to compare the London dispersion forces between, say, helium and argon, which one would you think would have higher London dispersion forces? A bunch of helium atoms next to each other or a bunch of argon atoms next to each other? Well, the argon atoms have a larger electron cloud, so they have higher polarizability. And so you're going to have higher London dispersion forces. And you can actually see that in their boiling points. For example, the boiling point of helium is quite low. It is negative 268.9 degrees Celsius, while the boiling point of argon, it's still at a low temperature by our standards, but it's a much higher temperature than the boiling point for helium. It's at negative 185.8 degrees Celsius. So one way to think about this, if you were at, say, negative 270 degrees Celsius, you would find a sample of helium in a liquid state. But as you warm things up, as you get beyond negative 268.9 degrees Celsius, you're going to see that those London dispersion forces that are keeping those helium atoms together, sliding past each other in a liquid state, they're going to be overcome by the energy due to the temperature. And so they're going to be able to break free of each other, and essentially the helium is going to boil, and you're going to enter into a gaseous state, the state that most of us are used to seeing helium in. But that doesn't happen for argon until a good bit warmer, still cold by our standards, and that's because it takes more energy to overcome the London dispersion forces of argon, because the argon atoms have larger electron clouds. So generally speaking, the larger the molecule, because it has a larger electron cloud, it'll have higher polarizability and higher London dispersion forces. But also the shape of the molecule matters. The more that the molecules can come in contact with each other, the more surface area they have exposed to each other, the more likely that they can induce these dipoles in each other. For example, butane can come in two different forms. It can come in what's known as N-butane, which looks like this. So you have 4 carbons and 10 hydrogens. So 2, 3, 4, 5, 6, 7, 8, 9, 10. This is known as N-butane. But another form of butane, known as isobutane, would look like this. So you have 3 carbons in the main chain, and then you have 1 carbon that breaks off of that middle carbon, and then they all have 4 bonds, and the leftover bonds, you could say, are with the hydrogens. So it would look like this. And this right over here is isobutane. Isobutane. Now, if you had a sample of a bunch of N-butane versus a sample of a bunch of isobutane, which of these you think will have a higher boiling point? Pause this video and think about that. Well, if you have a bunch of N-butanes next to each other, imagine another N-butane right over here. It's going to have more surface area to its neighboring butanes because it is a long molecule. It can expose that surface area to its neighbors. While the isobutane, in some ways, is a little bit more compact. It has lower surface area. It doesn't have these big, long chains. And so because you have these longer N-butane molecules, you're going to have higher London dispersion forces. They obviously have the same number of atoms in them. They have the same number of electrons in them. So they have similar size electron clouds. They have the same molar mass. But because of N-butane's elongated shape, they're able to get closer to each other and induce more of these dipoles. So just by looking at the shape of N-butane versus isobutane, you say higher London dispersion forces in N-butane, so it's going to have a higher boiling point. It's going to require more energy to overcome the London dispersion forces and get into a gaseous state. Let's talk about hydrogen bonds. Depicted here, I have three different types of molecules. On the left, I have ammonia. Each ammonia molecule has one nitrogen bonded to three hydrogens. In the middle, I have something you're probably very familiar with. In fact, you're made up of it, which is water. Each oxygen is bonded to two hydrogens. And then here on the right, I have hydrogen fluoride. Each fluorine is bonded to one hydrogen. Now, why are these types of molecules interesting, and what does that have to do with hydrogen bonds? And the simple answer is, in each of these cases, you have hydrogen bonded to a much more electronegative atom. Even though these are covalent bonds, they're going to be polar covalent bonds. You are going to have a bond dipole moment that goes from the hydrogen to the more electronegative atom, from the hydrogen to the more electronegative atom, from the hydrogen to the more electronegative atom. The more electronegative atom is going to hog the electrons. The electrons are going to spend more time around that. So that end of the molecule is going to have a partial negative charge, and then the ends with the hydrogen, those are going to have partial positive charges. Another way to think about it is if you added these dipole moments, you would have a net dipole for the entire molecule that would look something like that. So we are dealing with polar molecules, and the polarity comes from both the asymmetry and you have a very electronegative atom bonded to hydrogen. Oxygen, very electronegative atom bonded to hydrogen. So this end of the molecule is partially negative. This end of the molecule, or these ends of the molecule, are partially positive. For hydrogen fluoride, this end is partially positive. This end is partially negative. And so what do you think could happen when these molecules interact with each other? The nitrogen end right over here of this ammonia could be attracted to one of these hydrogens that has a partially positive charge right over there. Or this hydrogen, the partial positive charge, might be attracted to that nitrogen that has a partial negative charge. And this attraction between the partial positive hydrogen end and the partially negative end of another molecule, those are hydrogen bonds. And they are an intermolecular force that will be additive to the total intermolecular force from, say, things like London dispersion forces, which makes you have a higher boiling point than you would have if you just thought about London dispersion forces. And to make that clear, you can look at this chart. You can see all of these molecules are formed between period 2 elements and hydrogen. In fact, all of these molecules have similar molar masses: methane, ammonia, hydrogen fluoride, and water. If we were just thinking about London dispersion forces are proportional to the polarizability of a molecule, which is proportional to the electron cloud size, which is proportional to the molar mass. And generally speaking, as you go from molecules formed with period 2 elements to period 3 elements to period 4 elements to period 5 elements, you do see that as the molar mass of those molecules increase, there is that general upward trend of the boiling point, and that's due to the London dispersion forces. But for any given period, you do see the separation. And in particular, you see a lot of separation for the molecules formed with oxygen, fluorine, and nitrogen. These molecules, despite having similar molar masses, have very different boiling points. So there must be some other type of intermolecular forces at play above and beyond London dispersion forces. And the simple answer is yes. What you have at play are the hydrogen bonds. Now, some of you might be wondering, well, look at these molecules formed with period 3 elements and hydrogen, or period 4 elements and hydrogen. They also don't have the same boiling point, even though you would expect similar London dispersion forces because they have similar molar masses. And the separation that you see here in boiling points, this too would be due to other things other than London dispersion forces. In particular, dipole forces would be at play. But what you can see is the spread is much higher for these molecules formed with nitrogen and hydrogen, fluorine and hydrogen, and oxygen and hydrogen. And that's because hydrogen bonds can be viewed as the strongest form of dipole forces. Hydrogen bonds are a special case of dipole forces. When we're talking about hydrogen bonds, we're usually talking about a specific bond dipole. the bond between hydrogen and a more electronegative atom like nitrogen, oxygen, and fluorine. And so we're specifically talking about that part of the molecule, that hydrogen part that has a partially positive charge being attracted to the partially negative end of another molecule. So it's really about a bond dipole with hydrogen bonds versus a total molecular dipole when we talk about dipole-dipole interactions in general. And so you can imagine, it doesn't even just have to be hydrogen bonds between a like molecule. You could have hydrogen bonds between an ammonia molecule and a water molecule, or between a water molecule and a hydrogen fluoride molecule. And I mentioned that these are really important in biology. This right over here is a close-up of DNA. You can see that the base pairs in DNA, you can imagine the rungs of the ladder, those are formed by hydrogen bonds between base pairs. So those hydrogen bonds are strong enough to keep that double helix together, but then they're not so strong that they can't be pulled apart when it's time to replicate or transcribe the DNA. Hydrogen bonds are also a big deal in proteins. You learn in biology class that proteins are made up of chains of amino acids, and the function is heavily influenced by the shape of that protein. And that shape is influenced by hydrogen bonds that might form between the amino acids that make up the protein. So hydrogen bonds are everywhere. There are many hydrogen bonds in your body right now, mainly not just because of the DNA, mainly because you're mostly water. So life as we know it would not exist without hydrogen bonds. So I have these two molecules here, propane on the left and acetaldehyde here on the right. And we've already calculated their molar masses for you, and you see that they have very close molar masses. And so based on what you see in front of you, which of these you think would have a higher boiling point? A sample of pure propane or a sample of pure acetaldehyde? Pause this video and think about that. All right. Well, in previous videos when we talked about boiling points and why they might be different, we talked about intermolecular forces. Because you could imagine if you have a bunch of molecules, let's say in a liquid state, the boiling point is going to be dependent on how much energy you need to put into the system in order for the intermolecular forces between the molecules to be overcome so that molecules could break free and enter into a gaseous state. And so when we're thinking about which might have a higher boiling point, we really just need to think about which one would have higher intermolecular forces. Now, in a previous video, we talked about London dispersion forces, which you can view as random dipoles forming in one molecule, and then that can induce dipoles in a neighboring molecule. And then the positive end, even temporarily positive end of one, could be attracted to the temporarily negative end of another, and vice versa. And that whole phenomenon can domino. And we said that you're going to have more of those London dispersion forces the more polarizable your molecule is, which is related to how large of an electron cloud it has, which is related to its molar mass. And when we look at these two molecules, they have near identical molar masses. So you might expect them to have near identical boiling points. But it turns out that that is not the case. The boiling point of propane is negative 42.1 degrees Celsius, while the boiling point of acetaldehyde is 20.1 degrees Celsius. So what makes the difference? Why does acetaldehyde have such a higher boiling point? Why does it take more energy for the molecules in liquid acetaldehyde to be able to break free of each other, to overcome their intermolecular forces? Well, the answer, you might imagine, is other things are at play on top of the London dispersion forces. And what we're going to talk about in this video is dipole-dipole forces. So you might already imagine where this is going. In the video on London dispersion forces, we talked about a temporary dipole inducing a dipole in a neighboring molecule and then them being attracted to each other. Now we're going to talk about permanent dipoles. So when you look at both of these molecules, which one would you think has a stronger permanent dipole? Or another way of thinking about it is, which one has a larger dipole moment? Remember, Molecular dipole moments are just the vector sum of all of the dipole moments of the individual bonds. And the dipole moments are all proportional to the differences in electronegativity. When we look at propane here on the left, carbon is a little bit more electronegative than hydrogen, but not a lot more electronegative. So you will have these dipole moments on each of the bonds that might look something like this. So you would have these things that look like that. If that is looking unfamiliar to you, I encourage you to review the videos on dipole moments. But as you can see, there's a symmetry to propane as well. So if you were to take all of these arrows that I'm drawing, and net them together, you're not going to get much of a molecular dipole moment. You will get a little bit of one, but they, for the most part, cancel out. Now, what about acetaldehyde? Well, acetaldehyde, there's a few giveaways here. One is it's an asymmetric molecule. So asymmetric molecules are good suspects for having a higher dipole moment. Another good indicator is you have some character here that's quite electronegative. In this case, oxygen is quite electronegative, and even more important, it's a good bit more electronegative than carbon. So right over here, this carbon-oxygen double bond, you're going to have a pretty significant dipole moment just on this double bond. It might look like that. And all of the other dipole moments for all of the other bonds aren't going to cancel this large one out. In fact, they might add to it a little bit because of the molecule's asymmetry. And so net-net, your whole molecule is going to have a pretty significant dipole moment. It'll look something like this, and I'm just going to approximate it, but we're going to point towards the more negative end. So it might look something like this, pointing towards the more negative end, and I'll put this little cross here at the more positive end. And so you would expect a partial negative charge at that end and a partial positive charge at this end. And so what's going to happen if it's next to another acetaldehyde? Well, the partially negative end of one acetaldehyde is going to be attracted to the partially positive end of another acetaldehyde. And so this is what people are talking about when they say dipole-dipole forces. We are talking about a permanent dipole being attracted to another permanent dipole. And so acetaldehyde is experiencing that on top of the London dispersion forces, which is why it has a higher boiling point. Now, some of you might be wondering, hey, can a permanent dipole induce a dipole in a neighboring molecule and then those get attracted to each other? And the simple answer is yes, it makes a lot of sense. You can absolutely have a dipole and then induced dipole interaction. And we might cover that in a few examples in the future, but this can also occur. You can have a temporary dipole inducing a dipole in the neighbor, and then they get attracted to each other, and you can have a bit of a domino effect. You can have a permanent dipole interacting with another permanent dipole. They get attracted to each other. And you could have a permanent dipole inducing a dipole in a neighboring molecule.